morning, friends. We were discussing about the steps required to formulate 6 degrees of freedom equation of motion. And how did we start? We say that if you want to write equation of motion, then I need to use this d by dt of mv, that is external impressed force that is responsible for changing the momentum of a body, right? And also we did a simplification. We said this can be written as m dv by dt plus v dm by dt, right? And what is the simplification we did? We said dm by dt is 0. That is negligible change in mass. Please understand, we are developing these equations of motion for a specific purpose, for the purpose of dynamic stability analysis. And when you do this dynamic stability analysis, we are not doing for a longer time. We do for a small time. Maybe we need only data of 3-4 seconds, 5 seconds, 6 seconds, that's all. We should be able to immediately characterize, generally for stable airplane, whether it is dynamically stable or not. Okay. So, because the duration is small, we said we are assuming that whatever change of mass has happened because of fuel consumption, that is neglected. Okay. So, we wrote F equal to m dv by dt, and based on this we develop a further equation. We wrote F equal to m dvc by dt. Understanding was, whatever external impressed force is acting on the body, I can model it for a rigid airplane as if this is as simple as this external impressed force will change the acceleration of the center of mass. What is center of mass? Whatever the center of gravity we say on Earth, it is the point where all the masses can be assumed to be concentrated. Recall, we started developing this by assuming elemental mass, then did the summation, right? So, this is one understanding. Second, we got that external impressed moment, that is again that will cause rate of change of angular momentum. This was linear momentum and this is angular momentum. And from there, we got equations that this h, we try to develop how to derive an expression for angular momentum. We again followed that definition of angular momentum as r cross mv, right? And we again took delta m, then did summation. Last lecture you could see. So, after doing that, we got the expression h equal to p ix minus q ixy minus r ixz, then hy, this is hx, the component of h along x-axis. I will explain what is this x-axis. I will try to recall so that it goes deep into your mind. Let me first write, and hy we got as minus p ixy plus q iy minus r iyz, and hz, the z component is minus p ixz minus q iyz plus r iz. That is exactly where we ended our last lecture. So, I will go a little more into this so that you are clear what exactly is happening. One thing we should not forget, since we are applying Newton's laws of motion, we are defining everything, the velocity, angular momentum, all these things we refer to inertial frame, right? And in our study, What is the inertial frame? Is earth fixed inertial frame. So this is XE, YE and ZE. Why we are choosing earth as the inertial frame? Because we are assuming here that earth acceleration is negligible to the context what we are doing stability analysis. So we are assuming earth has no acceleration, or the acceleration is too insignificant to do anything with the stability analysis. So that's why we said we are assuming earth fixed, and we are treating it as inertial frame for the purpose of this study. Okay? And what is Hx? Hx is angular momentum of the airplane along x direction, that is along the unit vector IE, which is fixed. This is not rotating, right? What is Hy? Hy is angular momentum along earth fixed j direction unit vector, similarly k direction for Sz. And how did you develop this equation? That is also important. We are trying to go back and see how these expressions were obtained. Hx, Hy, Sz is the component of angular momentum along inertial frame, which is earth fixed, and unit vectors are IE, JE and KE, right? If you recall, what was the approach? This H we have shown to be equal to summation R cross omega cross R dm, right? What was R? Again, see, if this was the airplane, this is the wing. Just to recall, this is the center of mass, and what was R? R is the distance of mass element delta m with respect to center of mass, okay, or the center of gravity for our purpose. What was omega? Omega was the angular velocity of this airplane about inertial frame, correct? What was omega? So omega was, what we assume was angular velocity about inertial frame, which are having IE, YE, Z and KE as the unit vector. So if I write omega in terms of refer to inertial frame, I will write, say, omega x component, let us say P into IE plus Q, y component into JE unit vector plus R KE unit vector. Okay. What are PQR? PQR are the component of angular velocity omega along inertial earth fixed XC, YE, ZE axis, right? Okay. So this is clear. So now what we will do, we will try to see from here how do you get this expression. I will write the steps and you should do yourself. First of all, let us find what is omega cross R. Omega cross R would be, what is R? R is, R you know is x, let us say x IE plus y JE plus Z KE. Okay. Now omega cross R is what? You know, by vector algebra I write IE JE KE, and omega is P Q R, R is X, Y, Z. So if I try to take the cross product, omega cross R, this will give me omega cross R equal to, let me write, Q Z minus R Y IE minus P Z minus R X JE plus Py minus Qx k bar. How do I get this? We are trying to explore, try to understand how did we get this expression Hx, Hy, Hz, which are the component of angular momentum of the body along earth fixed xe, ye, ze axis system, right? Please go back to my lecture notes. The expression of H was given as summation r cross omega cross r dm, and you know r is x I e, y z d and j e and z k e. Now, if I take the cross product omega cross r, now you know I, j, k, p, q, r, x, y, z, and if I take omega cross r, I will get these three terms like this. You know very well how to do it. Take this, so the I, so qz minus yr minus j, if I cut this, it is pz minus rx. Similarly for k, if I do like this, this is py minus qx. Okay? So this is omega cross r. What are you supposed to find? R cross omega cross r. So for r cross omega cross r, this will be again very simple. Again you write I, E, J, E, K, E, you need vectors, and then it is r cross, so x, y, z, and for omega we write q, z minus ry, then this is minus pz minus rx, and let me write this a little separate here, ke, unit vector, so this will be py minus qx. Okay? Then you do this cross product, and then you will see that you will get an expression again by mechanically, just doesn't require any skill now. Simply you have to do a similar way, and then you will get whole expression h as, let me write this, summation of p y square plus z square minus q yx minus r zx dm, then minus again summation of p xy minus q x square minus q z square plus r y z dm, and third one will be plus summation r x square minus p x z minus q z y plus y square r dm. Clear? See, for example, if I take the first term, this I will take it out. So this will be I, and this into this into this, minus this into this. That is the procedure. This into this, minus this into this. So immediately you could see you get py square here, right? So accordingly you can develop, okay? But let us give an interpretation. What is summation of y square plus z square dm? You all know what is it? This is nothing but Ixx, right? Okay. Similarly, you find summation of yx dm. This will be cross moment of inertia Iyx. So accordingly, you can develop. So what we have seen, we now know what were the steps to get this hx, hy, hz, which are the component of angular momentum, or about the inertial earth fixed frame. Okay? And you are now smart enough to know how these terms have come. Please remember, you have to do once all this thing, then you can play around with the result. Okay? So put your time to see the what are the steps, how we got this thing, that clarifies so many things when you will be going for implementation. But remember one thing, we are all working so far in inertial frame, right? What is the issue? Now I will be discussing. Then we will try to justify why we need to work in body frame, and that will make our life more comfortable, right? That is the part now coming. So far we were working in inertial frame. What are the issues? See, suppose this is the body, okay? This is the airplane, and we are working with respect to inertial frame. Now, see, we have been using moment of inertia of the body when we were estimating, deriving the expression for angular momentum, like Ixx, Iyy, Ixy, Iyz, so many. But imagine, suppose this is the inertial frame, and it's fixed. I also imagine this inertial frame is same over here. Whatever way you think, let's say this is inertial frame, I can always see inertial frame at this point, which is fixed with the earth orientation, no change in orientation. Okay. Now what will happen? If the body moves, rotates like this, as the body moves, now see the moment of inertia about earth fixed axis system will go on changing, right? Suppose this is the body, and let's say earth fixed axis system is this, which is exactly what is on the earth, the way we have drawn there. Now if the body rotates, what is happening? This, whatever x axis was, earth is here, now the position of particle from the earth fixed x axis is changing. So moment of inertia will change. Similar thing will happen with respect to other axis also. So as the body rotates, and if we are doing all measurement with respect to a fixed axis, the moment of inertia of the body will go on changing with time. Moment of inertia will go on changing with time, right? If I explain here, suppose this body has rotated like this, okay, but your earth fixed axis is stationary, okay. Let's say this is x, this is, or to be more precise in the right system, the way we are doing it, let's say this is x, earth, this is y earth, this is z earth, right. Now as the body has rotated, the distance of the particles from the x, y, z axis is also changing. That is, if it was initially like this, if you think of a particle here, it has some coordinate with respect to earth fixed x, y, z axis. If it rotates, same particle now will have different coordinates. So its moment of inertia will change. That means I can say, as the body rotates, if I am working with inertial frame, its moment of inertia will go on changing with time, which creates a lot of complication for us for computation. This is one. Second thing is, we all know the aerodynamic forces. Dynamic forces, they depend upon relative, or more precisely air relative speed or velocity. Okay, so it has nothing to do with what is the speed with respect to the ground or earth fixed system. I have given you example. An aircraft could be on the ground. However, if there is a wind, it will generate or it will experience aerodynamic forces. So as far as aerodynamic forces are concerned, I will be more comfortable if I see what is happening with respect to, relative to any frame which is fixed to the body. Okay, I will not be comfortable in terms of if this velocity is with respect to the ground, because the forces depend upon the air relative velocity with respect to the body. So that also necessitates that it is better to work in a body frame. Clear? So two things I repeat. As I am rotating the body, or as the body rotates in free space, the moment of inertia of the body about fixed earth fixed axis system changes. So, we say momentum inertia will go on changing on time, that brings complication. And second point, because the aerodynamic forces depends upon relative airspeed with respect to the body, not with respect to the ground. So, I will be more comfortable to work with a frame which is with a body frame, and that is where what is done is we prefer working in body frame let us say this is XB, YB and ZB. This is the body fixed frame. That means as the body rotates, the frame also rotates. So, one thing, since the frame rotates, so in body frame the moment of inertia will not change with time, correct, because axis is also rotating. If it was with respect to inertial frame, then as the body rotates, inertial frame is not rotating. So, there will be change in moment of inertia. Now, if I work on body frame, as the body moves, axis also moves. So, moment of inertia will remain same, no issues. Second thing, if I am working in a body frame, I can get what is the relative speed of the airplane with respect to the medium. Okay? So, these two things makes life comfortable, and of course, it goes without saying this is located at center of mass or center of gravity for our case. Right. So, we have a desire to work in a body frame, it will make our life very comfortable. What is the problem? Let us see. It is good we want to work in body frame, that makes our life comfortable, but what is the problem? Problem is when you are applying F equal to d by dt m dv by dt or m equal to d by dt of h, that is rate of change of momentum, and we have neglected your dm by dt. So, this was, to be more precise, this was d by dt of mv, rate of change of linear momentum, and that we wrote as m dv by dt, because dm by dt was 0, because dm by dt assumed to be 0. So, we need to have a vector differentiation. In which frame? This should be in inertial frame. Please understand one thing. Suppose you are in a frame suppose there is a vector in this frame, okay, and assume that these directions are not changing, the frame is not rotating, okay. Its unit vector direction I, E, J, E and K, E are fixed, right. Now, see, if this body rotates like this, what will happen? What will happen is, and let us say this body is having velocity v, then the component of v along x, y, z will go on changing, right. So, when you say there is a rate of change of momentum along x, y, z, we can easily find out what is the component here, what is the component here, what is the component here, and take the derivative of that component, the scalar component. That will be the actually contributing towards the rate of change of momentum or rate of change of velocity. Okay. However, if you see this is the velocity vector, right, and velocity vector, let us say it is fixed here and this frame is rotating, then what will happen? Two things are happening if frame is rotating. One is the component is changing, scalar component, as well as because this unit vector is changing, that means there is a change di by dt, dj by dt, dk by dt, that is there is a rate of change of unit vector. Why? Because the direction is changing. If the frame is rotating, the direction of I, j, k are changing. So, vector is a different vector if directions are different. So, there is a rate of change of vector for our purpose, right. So, what is to be done is that if I want to really do this derivative, let's derivative of a vector in inertial frame, I will ask a question, can I still use this as an effect but operate in rotating frame? That is, I want to work in this body frame which is rotating, but I will ensure that it is equivalent to differentiating the vector in inertial frame. So what is the way to do it? Okay? That is the question you are asking. For example, if you see, if I am measuring acceleration of a body, let's say some axis system is there, I say it is inertial frame, so I know the whatever x distance is there, d square x by dt square is the acceleration. Correct? As long as this is inertial frame. But now, if this frame itself is accelerating, let's say with some AF, then whatever acceleration you are measuring with respect to this frame will not be the true acceleration. So what is the best way to get the true acceleration? That if I know frame acceleration, somehow I should absorb in this acceleration and correct this acceleration. Then I should get it. Okay? With this philosophy, we will now try to see how mathematically this problem can be handled through the definition of a vector in rotating frame. So what do we want? dA by dt, but I want to work in rotating frame, and I will just show that it's very well standard result, and that is this dA by dt inertial frame is equivalently can be handled by operating by differentiating in a rotating frame if you put appropriate correction, and that is dA by dt in rotating frame plus omega cross A. That is, you find dA by dt assuming there is no change in ijk direction, okay? Only scalar part. I repeat here. So what is the message here? The dA by dt inertial frame is equivalently, I can use and operate on a rotating frame if I get dA by dt in rotating frame and add this omega cross A. Omega is the angular velocity, of the frame. Let us try to understand it more, and I would suggest that let us see how this equation was, or expression was derived. Once we do that, you will find, oh, this is the thing. But the message is what? You need not differentiate the vector in inertial frame. You still can work in a body frame, rotating frame. If you, instead of this, you do this in a rotating frame plus add this, that's all. Okay? What exactly it means when we derive this relationship. Thank you very much.